Today we'll see about virtual B-trees and LRU. Okay. So what is a virtual B-tree? Okay, here we have seeing about techniques to handle an index file which is larger than memory. Okay, we had seen 2 to 3 solutions where we ended up with having some or the other problems. So the different way of handling larger files were that we tried with list, then we tried with binary tree, then we tried with B-tree, storing in the secondary device. Okay, these were the different techniques which we have used. Now here, after these, we are again introducing another technique of how to save an index file which is larger than the memory. Okay, so here we'll be mainly seeing about virtual B trees. Okay, first itself, before coming to the topic itself, we'll just see an example and then we'll see how does it improve our storage. Okay, so considering an index file which is having 1 MB records and the memory is 256 KB and the page size of one page is 4 KB. Okay, where it holds 64 keys per page. Okay, so we can tell that the B tree is actually of 3 levels. Okay, now we'll see how can my virtual B tree improve the space storage, okay, compared to B trees. So what is a virtual B tree? Virtual B tree is nothing but usually we have seen previously in memory, whenever we are going to execute a tree, what we do means we load the root, and thereby whenever we go for searching for the next node, we try reading the next node. Similarly, now here in virtual B tree we are having a concept that we try to manage a buffer, that is a space in the memory, and which is used for saving my pages. Okay, so for the first step is we create a page in the buffer. Okay, after that what do? We hold some number of pages inside this buffer. Okay, so first itself, before loading or using the B tree, we create a buffer which is ready to hold a page. Then we store a limit of 5 to 10 pages inside that buffer ready for the usage. And after that, how is the buffer being stored? Normally it is stored whenever a request is come from the user. Okay, so based upon the user request, every time it makes a request to the secondary device and reads the page. Okay, inside. Okay, if consider the case that when it goes to the memory and that particular page is not available, what happens? It goes back to the secondary storage and it loads it to the memory and then use it. Okay, that is the case. Okay, so what is virtual B tree? This technique of paging a list of pages inside my memory so that the page fault can be reduced is known as virtual B tree. Okay. Now, which are the different placement algorithms which is available here? Which we have already seen that if it is not available inside the memory, we try to read it from the secondary storage. In that case, some in the buffer already some pages will be filled. In that case, we are trying to replace a page which is existing in the buffer. So based upon what algorithm, the page replacement is done inside the memory. So we have mainly two techniques. The first one is LRU, that is least recently used. Okay, least recently used page which is available inside the memory is the first one, which is removed from the memory and replaced with the new requested page. Okay, and the second one is page height. Okay, the page height mainly represents the highly used page in the root node of your page. So that will be available within one disk access. Okay, so this is the two techniques. We'll see it here. The first one is LRU. In LRU, we mainly concentrate on page fault. Now, what is a page fault? If we have a request for a page, and if that page is not available inside your buffer in the sense inside your memory, in that case it goes to the secondary, gets it to the memory, then it's known as a page fault. That is, the page is not available inside the memory. Okay, now what are the two causes of page fault? The two causes of page fault is, the first one is it was never used, that particular page was never requested by the user, and the second case is when it happens that because of continuous request, the already loaded page was replaced by a newly requested page. In that case also we end up with page fault. That is the second case. So the first one is actually unavoidable because we never used a page, so there is no chance that the page has come inside, so it is unavoidable. That usually happens. And the second case is we have to use for solving that problem, we have to use some buffer management technique, like least recently used must be removed, so that the available page is maintained inside the buffer, and so that the disk access can be reduced. So we try to maintain that second problem or second cause by using least recently used replacement technique. Okay, now how does this least recently used replacement technique work? First itself, they make a track of every page, how many requests come for that particular page. They make a track of it. Okay, considering that when a new page comes inside and the buffer is full, they try to make they go through the number of requests of each and every page and comes to know that which page was requested least. Okay, according to that, the least requested pages removed and the newly requested page is replaced. Okay, so this helps you to avoid the unnecessary pages from the buffer. Okay, now the another solution for this is we can either try to improve the buffer area so that more number of pages can be used inside my buffer. Okay, we mainly use the principle of temporal locality. Temporal locality in the sense the need of a page is more likely more when the page has recently been used. In the sense, if a page is used currently, it means that it might be used recently. Okay, that is known as temporal locality. So we go for the next point, that is page height. As I've already explained, in page height we maintain a tree hierarchy telling that the highest page, that is the if the root page will be the page which is highly used. Okay, so it is available in the root itself, so that within one disk we are able to retrieve it. Okay, so now we go for the calculation of how much does my virtual memory help me with improving the disk access. Okay, for the same sum, with memory is having 256 kilobytes and index is 1 million bytes, then page size is 4 kilobytes and the buffer is able to hold 64 pages. Okay, now consider that I need to save 1 megabyte of data, okay, inside my memory. When I'm storing that 1 megabyte into the disk, it happens that because of fragmentation or any other additional separators which we use, delimiters which we use, it happens that my disk might use 1.2 megabytes of data. In that case, how much data I must be, or how much pages I require to save inside my memory? For calculating that, I need to do 1.2 into 10 raised to 6, that is 1.2 megabytes. 10 raised to 6 divided by the division of number of pages. How many bytes does one page contain? It contains 4 kilobytes, so it is 4 into 10 raised to 3. So the total number of pages for saving 1.2 megabytes of data is 300 pages. Okay, that is, we require 3 levels of tree for saving my 300 pages of data. Okay, so we can tell the root will contain 1 page, the second level will contain 9 to 10 pages, and the other rest pages will be inside my leaf level. So here, when I'm considering my page height, I'm trying to introduce both the techniques, that is least recently used and the page height. When I'm trying to use both techniques, I see that the average number of access for a data is reduced. So how is it being reduced? In the case of a 10-page buffer, I can see that the efficiency have improved from 1.42 access per search to 1.12 access per search. Okay, so this is the improvement which we see when we introduce the technique of least recently used strategy and page height. So we come with the concept that again, that virtual Btrees helps us to introduce or helps us to improve the system performance, because we are able to handle the number of pages inside the memory efficiently. Thank you.